All right, so just to make sure we're all on the same page, all right, I'm going to write this down. So on ELC, there is a final exam folder, and if you guys can't find any of this stuff, email me and I'll go back and double check, but I'm pretty sure I posted all up. So right now, there's the Chapter 6 review packet. That goes with the videos, all right? The videos are on YouTube. And I'm pretty sure in an email to you guys, or I might have even on ELC in that folder, I could just post the link to the playlist. So I'm pretty sure the link to the playlist there, if it's not, I can add it when I put these other files up tonight. So then this is up there now, all right? So then tonight, you'll see the Chapter 6 stuff hit. That will also have, it'll be a review packet that you can print out and fill in. And I really do recommend taking the time to print it out, fill it in, because like I said, this thing was designed so that way you can use it as a reference later. If you ever need to go back and review anything, and then that'll be up, the video for that'll be recorded tonight, and that'll go on YouTube. Yep, I did that the same thing in my last class too. All right, so then this stuff will be due at the final exam. So it's I'll just give you until the day of your final, since it's the last day of finals, to turn it in. And so the take-home practice problems will be, they will serve as your exam 1 grade and your exam 2 grade. So you get to, you get plenty of time, and they'll also be good for studying. You guys will have a different version of the final. I haven't forgot about that. So your exam 3 stuff will be the same as everybody else's in my class, but I will just have slightly different problems for your Chapter 6 and 8. Just, just very straightforward, nothing kind of crazy, because you just got to make sure you understand the mechanics of how to do this stuff. One thing to look out for is once you get to the final, right, we can combine like Unit 1 and 2 stuff. So what I mean by that is like when you're rotating a graph, right, around, like when we did shell or disk, when you first learned that, well, you didn't know in theory how to do any of the trig integrals yet, or you didn't know integration by parts. So one of the things that we can do, because you don't have time to do a lot of computation, is you can combine the two concepts. So you can now like rotate like sine squared of x or something like that around. But any, I have on ELC as well, I have a worksheet that's just basic graphs you should know, okay? If it's anything like weird or abnormal, I will draw the region and give you the region drawn. But like if it's something like y equals x, you have to know how to draw that. Like you're supposed to know how to draw a quadratic. You should be able to sketch a cosine or a sine wave. So if there's any regions you have to sketch to set up the problem, that's kind of how I do it. But sometimes I'll give you the region, sometimes I'll ask you to draw the region, but I'm usually pretty fair. Your final is going to be December 13th, that's Wednesday, at, I believe it's 3:30 p.m. So it'll be 3:30 to 6:30 in here. Right, room 300A. So if for some reason that you're one of the, there shouldn't be any conflicts, but if the final just for some reason falls in conflict with another final just because of how weird all of this has been, if needed, I will allow the transfer students, which this is Tuesday, at noon to 3. If you need to take it the day before, you can take it with my other class. So if you plan on doing that, though, you need to let me know, because seating's limited in there, and so I can accommodate probably about 6 or 7 people, but anything beyond that, we're going to run out of seats. So if you fall into this category, just let me know. And this is Hardman Hall, room 102. So I just need to know if you decide to do that. I will organize the final in a way, because I just think this stuff's hard enough. I will make sure the problems in the final are grouped by unit. So it'll be the Unit 1 material, then the Unit 2 material, then the Unit 3 material. Just mixing that stuff all together is crazy. I don't see the point in sandwiching a series in between 2 integral problems, because it's just, kind of headspace. So if you need to like work around and work the final in different pieces, like if you want to do the sequences and series stuff first because it's fresher in your mind, and then go back and work on those integrals, that's fine. Definitely go back and look at the old exams online, and the keys are up, because that's a great indication of level of difficulty. You'll notice that not all the problems, you don't finish them all. Some of them were like set up but don't complete because the algebra steps just take too long. So the reason we do that is what's most important about the Unit 1 and 2 material is, do you understand the methodology? Do you understand the components required to set up the problem? But it's just not possible to have you work all of that stuff out to completion. But yeah, definitely look at the old exams first. And if you're looking for practice problems to do, work on those problems, and you can see the key is written out for you. As far as test 3, somebody asked me in my last class, which I thought I said this before the exam, you'll see the key for exam 3, but some of those, when I wrote the problem, I just did the most obvious test that I saw. But some of those problems, there was more than one legitimate way to do the problem. So if you picked a different method than what I did and it's correct, you'll get full credit as long as you did it the correct approach. So don't assume that just because I used a specific test on that problem, that's the only way to prove convergence or divergence. So if you did something different, like, don't freak out unless it was just wrong. But yeah, sometimes on there, you'll see more than one way to do a problem. So do you guys have any questions for me about the exam or anything like that?
How many questions is it going to be?
I don't know how many are on the final because I'm having to rework it. I'm not quite done writing it yet. I'm not exactly sure how many you guys are going to have, but it's usually the multiplier is like 2 to 2.5 times the length of a normal in-class test because you have 3 hours. So usually it's usually double. It's usually like about 2 exams, the length of 2 exams. So, and what you'll see is Unit 1 and 2, there's a lot of combination you can do with that stuff. So that's how you can reduce it down, and then we obviously will have more sequences and series. And I'm still going to make a packet later over the break for you guys for the vector stuff because, I want you to learn vectors from me, but I just don't see the point adding another log on the fire. You guys just already have too much that you have to account for. It's been kind of a crazy semester for all of us. And then I'll be at the cabin. I leave Wednesday night to go out of town. I'll check my email once a day. I'll be at the cabin and I'll just be grading the whole time I'm there. So as soon as I get the exam 3 grades done, I'll throw those on ELC. And then rather than typing in all the individual quiz grades, what I'll do is I'll just put your quiz average for those. And then on the day of the final, I'll give you back all your graded work. One last thing. I will have office hours. So tonight's my last science guys night for the semester, so I'll be working late till 8, and then I'll have to go back and record for you guys. But Tuesday, tomorrow, even though we're on a Friday schedule, I will be in Millage Hall from 6 to 9. So that's the Millage Hall Math Lab. And then Monday, December 11th, from 10 a.m. to noon. And usually what happens is if we have a good turnout, we'll usually end up pushing it about an hour beyond this if there's people there and studying. But I just tell people, I'm like, don't roll in at 11:45 because if everybody's winding down with like 20 questions, at 15 minutes left of office hours is kind of but usually we're going until about 1. So we're going to have these at Walker's Coffee. It's on College Avenue. Downtown, right across from the Arch, so you can park on campus. But I just really like to do off-campus office hours during finals, just so we don't have to compete with everybody. But they have it downstairs, and it's got booths and a big bar and lots of bar stools. So it's just a great place. It kind of works as a great study hall, and they're really nice, and they kind of let me always grab a block of time and just kind of take it over for a few hours. So it's a nice little study hall. So those are always been good. But we can just kind of do some final cleanup on any questions people have, and you'll meet other people from your class, everybody work together. And so I always open a tab, and I always say everybody needs study fuel, so I'll buy your first coffee or tea drink on me, just no booze. But actually that early in the morning they don't serve anyway. But yeah, I always get ready a coffee or a tea or iced coffee or something, and we just kind of hang out down there and study for like 3 hours, and it's usually pretty fun. Everybody has a good time. So that'll be my office hours. What else? Okay.
Will we get our exam 3 back?
Yes, on the day of the final, I'll have all that stuff back. Great. And actually, I'll bring, what I'll do is I'll try, because I'll have it all done when I get back from the cabin. What I'll do is I'll bring all of it to office hours. So if you come to those Monday morning office hours, I can give you stuff then too, so you can have it to look over before the final. Yeah, so anybody have any questions about the test that you just took? No? All right, well, you guys kind of need to tell me what you want to talk about, because we got today and tomorrow to look at anything you want. We can do any kind of problems. We can look at examples of problems. I've got the book if you want to, I mean, we could definitely do a shell problem together since you guys didn't see that in a real life class.
Can we also do an example of like finding the sum?
Finding the sum of a series, yeah. And so remember, there's only two things you can sum, right? Telescoping and geometric. Those are the only ones we can ask you to sum. So if we just say find the sum of the series, you know you're working with one of those types. And most of the time those are geometric, right? Because we don't really do a whole lot with telescoping, but yeah. So yeah, we can do a shell disc washer problem and kind of show you guys how to walk through that so you can ask some questions, because I do a bunch of stuff on the video. Yeah, let me pull up the book. Let's see. All right, so we'll do something really generic and then we'll do something a little more fun. Okay, yeah.
Okay, this probably, like, seems like a dumb question, but so what's, like, the point of what we're about to do? Like, what are we doing? You know what I'm saying?
Yeah, okay.
Like, I feel like I never got to, like, put it all together.
Yeah. So, disc, washer, and shell. So those first two sections in the book. What you're doing is you're trying to find, right, if you just take the integral of any basic function, what you're doing is you're finding the area under the curve, okay? So it's actually a geometric reason we do that, right? And so like in statistics, for example, the application for area under the curve is probability that an event happens. So you integrate from one part to another and that tells you the probability. But if you take a function and you rotate it around the axis and you integrate the area of the cross section, you can actually find the volume. So if you're ever curious of where did the formula for the volume of a cylinder come from, right? Well, that one's pretty basic. You just take the area of the circle, the base, right, and multiply it by the height. But what you really were doing there, if you actually look at the derivation of those formulas, is you were taking the cross section, which was a circle, and you were integrating across the height. And so when you do area times height, you get volume, right? So for a cube, right, it's just x times x times x, right? Base times width times height. But what if we want to find the volume of something kind of more interesting? So like look at something like this, right? If I take this and rotate this line around this axis, right, I get something that might look like a funky little vase or something, right? And so what we can do now is we can find the volume of all different kinds of irregular shapes. We can make the profile look as nutty as we want it to be, as long as we understand what the cross sections look like. So for disc and shell, the cross sections are always going to be circles, okay? So for disc and washer, you'll either get solid discs, right? So that's just pi r squared. That's why if you look at the formula, it's just pi r squared across the height. And in this case, your profile here, right, you'd get circles around here, but you're integrating across this function here, and that's going to give you it's not a straight line anymore. Because if it was a straight line, we could just multiply by height, right? So with shell, what shell does for disc and washer, right, the height of this function right here is actually the radius. So you're going to get these solid circles. And so using disc and washer, we say, well, to get the volume, right, you integrate the cross section of the area across the distance of the function, and that's what gives you the volume. So since all of your cross sections are circles, the formula is, right, pi r squared dx. So you're just taking the area of the circle, and what's going to vary is the radius, because you can see here, if we drag this line from left to right, the radius gets taller or smaller, right, depending on where we are on the function. So that's why you write the radius as a function of x. So for this particular picture that I drew, the radius is simply always going to be equal to the function we drew across, because that's what you measure from the x-axis up to the function. That's just the height of the function, right? Shell method is a little different. So in shell method, we actually, this profile I drew, shell method wouldn't work. So let's look at something really simple. Let's look at the function y equals sine of x from 0 to pi over 2, okay? So sine of x goes to the origin, and it hits its peak at pi over 2. So the region in question is this, right? And if I want to spin this around the x-axis, right? A radius, by definition, goes from the center out, and a radius is always perpendicular to the axis of rotation. That's how a radius in a circle works, right? Except the center is just in the center of the circle, and those radii are always perpendicular in all directions out, and so whenever the radius hits the edge of the circle, it's actually perpendicular to the edge of the circle. So the radius of this function, right, is just here. Well, that distance from the x-axis up to the function is just the function itself. So our radius is sine of x, but the formula says we have to do pi r squared. So then the next thing you're supposed to do is square the radius. And if we want the volume of the solid, it's the integral of sine squared x dx. So when you were learning this in Unit 1, you technically at the time did not really know how to integrate sine squared x, right? Because we hadn't gotten to the trig integrals yet. But to integrate sine squared x, we sometimes throw this into the mix as kind of like a sneak peek. There is a trig identity that lets you rewrite sine squared into something you can integrate. And so we used it in our example in sequences and series when we wanted to find the series of sine squared or cosine squared. So sine squared x can be rewritten as 1 minus cosine 2x over 2. And so what this does is it takes the power from a square down to a single power, and that's something you can integrate directly. So if you wanted to actually work this problem out to completion, and since this is all over 2, I'm just going to pull the 1/2 out front. So this is something we could integrate directly, right? So we can finish the problem like this. So one of the things about disc and washer is they're actually the same thing, okay? They're identical. The only difference between the two is whether you have a hole in the middle of the thing or not. So what I always tell everybody is look for the gap. If the region is nice and tight against the axis of rotation, which this one is, when you spin it around, you're not going to have any gaps. You're going to get solid circles. So you only have to integrate pi r squared. But if we wanted to rotate this region, the same exact region, if I want to rotate it about the y-axis, well, look what happens now. There's a gap right here. So when you spin this around, what's going to happen is it's going to look like a cylinder on the outside because of those straight edges, but on the inside, you're going to get this funnel-like hole in the middle. So if you slice the cross sections across this way, because right, we're spinning it around like this, the cross sections are going to have a hole in the middle. And so that's why we actually say disc and washer are the same thing, except now you have 2 radii you have to identify. So if you want to find the area of the cross section, we take the area of the bigger circle and we subtract the area of the smaller circle. So the volume here, and this would actually be a function of y, would be pi capital R of y quantity squared, right, minus little r of y squared. So notice here, one of the things people mess up in this formula all the time is they'll subtract little r from big R and then square the result, and that is not right. You have to take pi r squared of the big circle and then subtract pi r squared of the inner circle. And so since they both have a pi attached to them, we just factor the pi out front. That's why we write it like this. So if you look at this picture here, well, r of y, right, little r of y, there's the radius of the hole. It just goes to the function. But big R of y goes all the way out to the outer edge. So for this particular equation, well, big R of y is just pi over 2, because that is the distance. You're just always going across pi over 2. But little r of y is going to the function, and so in order to write this, you can't use sine of y. This isn't sine of y, this was sine of x. So if you simply solve y equals sine of x for x, you now have a function of y. So this would be arc sine of y, right? You just take the inverse sine of both sides. Well, we could square this, right? We would get pi squared over 4, and then we could square arc sine of y, but you can't integrate that directly. Nobody knows what the antiderivative off the top of their head of inverse sine of y is, right? So, in speaking in terms of just geometry, right, in theory, the washer method would work with this problem because we're definitely getting washers as our cross-section, but when you go to set up the integral, the algebra's got you stuck. Does everybody see that? So, this is where the shell method comes into play. Washer just won't work when you rotate around the y, right, even though it looks like it should, because you get stuck in the math. So, the shell method, what it allows you to do is it allows you to switch to the other variable, all right? So if I want to try to do this same exact region in terms of the shell method, here's what would happen. And in terms of why you would want to do this in the real world, right? Manufacturing. If you're running a plant and you've got everything automated now, everything works on robotics. That's why they need computer scientists and engineers, in manufacturing, right? And you're building something or you're 3D printing something, right? You have to be able to program the equations in, but you also need to know, well, how many materials do you need to order? What's the volume of, whatever thing you're printing in, right? And so this is the kind of stuff where you can draw a profile and actually measure around, and you can design all kinds of shapes. And we actually have 3D printers on campus that you guys, I think some of you in the engineering program probably have some over there too, but you can actually draw something, design it, and print it to the computer. So if you understand all the different ways you can design something and spin it, a lot of computers are able to read stuff like this. So you can actually tell it, take this line, spin it around this other line, and here's the bounds on the line, and now give me the dimensions, and here you go. And then, or you can do an integral and very quickly calculate exactly what the volume is of the stuff. And I did an example with no numbers in it in my class where I showed the band, like if you took a sphere and you drilled a hole in the middle of the sphere, and we just looked at like a napkin ring kind of shape around it, we were able to derive the volume in terms of the width and the height without actually using any numbers in the problem. And then I was like, yeah, so if you wanted to make this thing, you could make it tons of different sizes, you could create a spreadsheet, you can pop all the different possible radii, all the different possible heights you want, and then by doing that one integral up front and figuring out what the formula is, you can then design, and then you can put in prices and figure out what it's going to cost, and you can do a cost-benefit analysis very, very quickly by just knowing what these dimensions and how much volume of that particular topic is going to need. So when you're in the real world and doing applied things and you're trying to figure out how to build something, what material to build it out of, if you've got sales and deals and, are we better off buying this in bulk or should we go to this deal? I mean, this stuff marries with spreadsheets and business and all that stuff. So this is not just complete arbitrary useless crap, all right? When my husband and I remodeled our house, he's got very expensive taste. And so he wanted to do this custom tile wall in the shower. So once I saw the layout of his design, I set up a formula and I was like, okay, well, you want 4x4 tiles on this area. So that's the surface area we need. Plus, you always put the 10% breakage in it, right? And then I was like, okay, then you want your border. So I had a formula for that. And then I knew that the style he wanted on top. So when we went to Lowe's, all he had to do was lay out his design, and all I had to do was pop the prices into a spreadsheet I made, and I could be like, well, that's going to cost $1,500 just for the tile. He'd be like, okay, what about this one? I'm like, well, that's going to cost this. That's going to cost this. Because once you knew, right, the dimensions. So this stuff is really, really applicable in the real world, all right? So don't ever think this is just some weird stuff. All right, so what does the shell method do? So the shell method, what you got to think about this is, you guys ever seen Russian nesting dolls? Those are, you pop the head off, there's another doll inside, another doll inside. Okay, so where disk was slicing it across this way, right? And we were adding up the areas of all the little circles we were creating. What the shell method does is think of it almost like when we rotate this around, right? On the other side, right? When we spin it around, you're going to get this in profile. So what the shell method does is think of it like a cookie cutter, right? That's got the cross section of a circle. And what you'll do is you'll slice it here. And then you'll have a little bit wider one, and then you'll have a little bit wider one, and then you'll have a little bit wider one. So what'll end up happening is you'll get these thin cylinders, and they would all nest inside each other like Russian nesting dolls and create the solid surface. So if you pull out one of the shells and you unfold it, right? So the shells would have width like dx or dy, right? So they look like little tubes, right? And then you would have another one inside of there, and another one inside of there, and another one inside of there. If you take a tube, right, and slice it down the middle and unroll it, you actually get a rectangle. So that's what you need to make the sides of a cylinder. You need a rectangle, okay? The height of the rectangle, right, matches the height of the cylinder. But the length of your rectangle is actually the circumference of this circle right here. So this is 2 pi r. So what we're actually doing with this integral is instead of adding up circles, we're actually adding up the area of these rectangles. So we'll make all the shells, then we, in theory, unfold them, stack them up, and add their area together. So the volume using shells is 2 pi r of x h of x dx. So the radius could be sometimes expressed as a function of x, and the heights can be expressed as a function of x, okay? So for this particular problem, right, we said washer wasn't going to work because we couldn't do the algebra to integrate. But the way this works in shells, the way you draw your picture, is the heights run perpendicular, or excuse me, the heights are parallel to the axis of rotation, and the radius is still perpendicular to the axis of rotation. So you pick any arbitrary point on the region, right, and there's your height, okay, for that particular shell. Now, notice how that's drawn. It's going from the x-axis up to the function. So that is just how we define some function f of x. So the heights of this region are just going to be sine of x. And you can see as you move this across left and right, you're just always going from the x-axis to sine of x, right? The radius at that exact spot, right, is measured from the axis of rotation over. So how do we define the distance from the y-axis to a point on the positive x-axis in terms of x?
Solve for y or solve for x?
So if so here, think about this. If I take this guy and trace it down, what's right there? It's just x. Right? When you're reading a graph, right, if you go from the x-axis up to the line, right, that's f of x, that's the height that comes out, right? But if you read across from the y-axis over to a point on the x-axis, those are just the x values you put in, right? So if I put whatever arbitrary x value this is between 0 and pi over 2, when you plug that into sine over x, it gives you the appropriate height. So r of x is just x. If it was a function of y, right, then that r of x would have been some function of y, right? But you notice I had it in terms of x. So what you can see here is on disk and washer, the variable matches the axis of rotation. So if you're using a horizontal axis of rotation, you're in variable x. If you're using a vertical axis of rotation, you're in variable y. But because with shell, everything's defined off the heights, which run parallel to those axes, it allows you to work in the other variable. So when you're going around the y-axis, this volume now of this solid is 2 pi from 0 to pi over 2 of x sine of x dx. This is another integral that you would technically not have been able to solve. It is solvable. It's actually a very easy integral to solve, but you would not have been able to solve this in Unit 1 because we hadn't taught you integration by parts yet. But this is a very straightforward integration by parts problem. So I'm kind of purposely not working these problems out to completion, because once you get a chance to watch the videos and see the techniques, these are great example problems for you to go back and like revisit and try. And this is a very straightforward integration by parts problem. So the question was though, right, they're all doing the same thing for you. Shell, disc, and washer, all they're doing is giving you the volume of a solid. I did a problem in the review. We're under disc and washer, we did it. And then in the shell problem, I did that same exact example again and showed you how you would get the same exact area if you did shell. So sometimes both methods will work. But the number one question that we always get asked is, how do I know which one to use and when should I use it, okay? And so there's sort of two big things that'll drive you to the right direction, all right? One of them, right, and this table's in your packet as well. So what you want to think about when you're doing disc, washer, and shell, all right? You can either have a horizontal or a vertical axis of rotation, right? So we can use the disc washer and we can get shell, because the whole game is trying to get volume. So for disc and washer, we said that the variable matches, right, the axis of rotation. So here all we're doing is integrating area of the cross section, right? In that case it was pi r squared. Here this would have to be in variable y. Shell lets you flip. So now these are in variable y. And these, oops, that should be a y. And these are in variable x. So I just showed you an example of a problem where on the surface, by the region, washers should have worked fine. They were definitely washers. We could define little r and big R, but when we went to set up the integral, we got stuck by the algebra. We couldn't integrate inverse sine of y, okay? So if you get in a situation where the function can be maybe solved for x or y, right, but you can't integrate that function, well then that tells you you need to go to the other variable. So switching methods allows you to switch the variable. So sometimes algebra is the reason. And I did an example in the chapter 6 review packet where I gave you a function that looked like this, right? We said rotate this function about an axis. Well, you can't solve a cubic for x. So you are stuck in variable x here. You'll never be able to write this as a function of y. So right off the bat, I know I'm stuck in variable x. So then the question was, well, do I have a vertical or horizontal axis of rotation? If I have a horizontal axis, well, then I need to use disc washer. If I have a vertical axis of rotation, then I'm required to use shell, right? So that was algebra getting in your way. What if the region itself is getting in your way? So if you look at the region, and let's say we have something like this. Let's say we want to rotate y equals sine of x, but now instead of only going to pi over 2, I want you to go all the way to pi, right? Well, if you go all the way to pi, it wraps back down and comes back to the x-axis. So if you want to spin this guy around the y-axis, well, it would be a washer if you tried disc or washer, but how do you distinguish between little r and big R? Because little r would be the hole inside, and big R would be right over here. But how do I write that as a function of y when it's the same line that both things are happening, right? You see that? So you can't separate the two r's out. So once again, I'm like, oh, I gotta work in x. So if I'm gonna have to stay in variable x, well now we would switch and we would have to use the shell method to do this, okay? So sometimes the region won't allow you to do one method or the other, and then sometimes it's the algebra that gets in your way. Now in this case it was both. Not only would the region not let me distinguish between my two r's, but I also, we already said, you can't integrate inverse sine of y. If we tried to switch that to variable y, it wouldn't work, right? So this is why they are doing the same things for you. They're just giving you volume of a 3D object, but we have two methods of doing it, and it's so we have the ability to switch to the other variable if we need to. So this one would be, shell would be required. And so that means the heights would just be the function themselves, and r of x in this case would just be x again, because I'm just rotating about the y-axis. So does that kind of connect the two ideas? So it's just kind of frustrating because you guys only got like half the story, you know, and I would say probably a fourth of the story. So, you know, there is an important reason we do this. It's very, very useful. And, you know, what's really even nutty, when I took this stuff for the first time, you know, 22 years ago, we didn't have all the technology we have today. And what's actually ironic about this math and doing all this stuff by hand is the more technology we have, the more applicable this actually is in like the field now. Like you can design car parts, you can design, I mean, you know, you can design something and just print it out, you know, and you can sketch. And so what's really awesome is if you can define those lines by actual equations, it's really easy to program an equation into a computer rather than having to draw it and sketch it and kind of doing it the old school way that we did it. So if you can identify the type of curve that you want to use, the angles, I mean, you know, you can really do a lot of cool math now and really push the limits of things further than we ever kind of did before with stuff. So does that kind of explain that? And then on the video, I go through lots of examples. I work them all out from start to finish, and then I gave you guys some problems. And so one of the problems that you have to do is I give you a region, and I want you to compute the integral in variable y. And then I also want you to compute it in variable x. And so you'll see that you're actually going to work that problem like 4 different ways. You'll do the shell method twice, and you'll do the disc washer twice, because by me switching the axis of rotation, it's going to change the method that you have to apply. And so this table right here is really, really helpful to figure out what variable matches what method for what type of axis of rotation. Right? And so one of the things you want to make sure you're doing when you do the problem, even if I give you the region, if you don't have the region, you need to draw the region, you need to label on the region where these things are, and that will very quickly enable you to come up with the equations that you need to do it. And so hopefully by this point you know how to read a function versus reading whether it should be an x or y, stuff like that. So these aren't too terrible to do. All right. So let's just look at like an arbitrary shell problem and just kind of set it up and do one where we have to kind of draw the region. So I had one pulled up I wanted to do. But did that answer the question about what we're doing and why? Okay. And so I'll hear a lot of people say shell's easier. I don't know why they say that. I think it's just because people freak out when they have to square things. But it's not always true. There are problems where shell method would be the harder method. The disc method is a more direct result, you know. But like I said, some can be done both ways, and some can only be done like one way or the other. Oh, I know the problem I wanted to show you guys. There's one on here that's really good where you have the region and you have to decide what method is appropriate. But let's do something like this. So let's do one where we have 2 different graphs that we're bounded by. All right, but I want to look at this problem first. Okay, so I usually do this one in my classes because I really like this problem. All right, so we have this region right here, and the equation is this. Okay, now this is not something I would expect you to be able to draw on your own. Like you would be given the picture with this, so don't freak out. But we want to draw this, we want to rotate this around the x-axis. So we're not actually going to work this out. This is more of kind of a strategy type thing. So what method do you think would be required for this one? Do you think we could do disc washer, or do you think we would have to use shell? Okay, so if you want to use disc washer, right, well there's your R, there's your big R. It's the same line. The region won't let you use disc and washer, right? You can't distinguish between the functions, all right? Also, this could actually be solved for either variable. So we could, in theory, algebraically, we can work with either one of these variables, x or y, right? But for the shell method, right, there's our height. So that would be a height, that's a function of y, And then in the same way, we call the radius x, the radius here is just going to be y. Because you go up to some arbitrary y value, and when you plug that y value in, it gives you the distance across, which is the height. So if we wanted to set this up, right, we have to say shell is actually required for this one. You can't do it using disk or washer. It just won't work. All right, let's look at one more region. And I think what we'll do tomorrow is I'll have some good problems. I'll show you some we'll look at some Unit 2 integration technique problems. So we'll do some like integration by parts and some trig stuff just to kind of get so you guys can ask questions about that stuff. All right, so here's the region. We want to rotate about the y, right? And here's the function. So what method do we think we should do? Well, actually, let's just start here. What variable do you think is going to be easier to work with, x or y? Well, if you want to work with y, you have to solve that for x. So if you solve an e to the x, you're going to get you're going to get log or natural log, right? And remember, the whole goal is to integrate. So is it easier to integrate e to the x, or is it easier to integrate log of y? E to the x, right? So algebraically, right, and that's one of the things where you want to know the relationship between function and their inverses. If you switch variables to the other variable, that means you have to do the algebra to solve, so you're going to turn that into its inverse. So an e would turn into a log, right? A square root, if you switch variables, you square both sides, so that would be better, right? But if you had a y squared, and you wanted to switch over to x and you solve for y, right, you would have to take the square root. So just remember, you're going to have to do the inverse algebra to get the other way. So x is actually much easier. The region is fine here. Like from a geometric standpoint, washer, disk, shell, well, it's no washer, it's disk or shell, would work fine. We can easily identify all the components. However, variable x algebraically is going to be what I'm going to be stuck in. So if you have a vertical axis of rotation, for disk and washer here, we would be in variable y. But the shell method lets us work with variable x. So shell would actually end up being required on this one because of algebra. So the previous one, shell was required because of the region. We couldn't define our r's the way we needed to. Here, we can define everything, but we wouldn't be able to integrate, right? Unless we stay in variable x. So that's the idea here when you're doing this stuff, is you got to have like a plan. You can't just dive in, and there is a reason why we prefer one method over the other. But I agree, when you see problems done in class, everybody just like does them, and it just feels like magic, and they always get there the right way, and you're like, why did you make the decision that you just made just there, right? So sometimes it's algebra, and sometimes it's geometry. That's why we do one method over the other. All right. Okay. Try anything else what's in Unit 1. So we do that, then we do arc length, and then we do surface of revolution. So I do want to give you, right, so this is why this stuff feels disjoint. So the first two sections, we're finding volumes of 3D solids, right? Then in section 3, we do arc length. All right. So arc length is when you want to find, right, the length of a curved path, right? And so if I'm sewing and I have one of those flexible tape measures, right, you could take it and bend it along the curvature of the function, and then when you're done, stretch it out and see, right, what the tape measure says, and that would give you the length. However, we derived, and on the video I actually run through the proof and show you, we derived that there's an integral we can do from A to B, and it will grab the length of the line everywhere, right? So why would this be important? Well, in physics, you have a lot of things that are path independent, where only thing you care about is the start and end point. It doesn't really matter how you get there. But then if there's a non-conservative force like friction or something else at play, you have things that we call our path dependent. So you actually need to know the length of the path that the particle moved on. So a line integral will allow you to do that. You can actually get the length of the line, right? So what we do here is there are 3 ways you can calculate this, right? So we can say, well, we can do it in variable x. And I derived this formula for you on the video, so I'm not going to run through the proof now. But what we do is we say, well, if we want to do it in variable x, we use the x endpoints, right? So this is point, I'm going to call it AC, and this is point BD. So because I'm working in x, I'm only grabbing the x values of the start and end point. And we take the derivative of the function, square it, add a 1, and we integrate. Now in Unit 1, there were a lot of these integrals we couldn't finish because you only have two options when you have the integral of a square root. You better hope the stuff inside of it can be factored into something squared, so then you can eliminate the square root, or you hope that you can do u substitution, right? But a lot of times you're not going to be able to do u substitution because if you have 1 plus x squared under there, well, the u substitution will require a 2x, right, for your du, and you don't have any extra x's outside of this guy. So a lot of these problems, you'll notice, are like set up but don't finish, okay, when you see them on tests and things because you can't physically finish them, right? If we want to find the length of this same line in variable y, well, hopefully for obvious reasons, the indices of the integral switch to the y components, right? You want to go from the lowest y to the highest y. But, and this is why this is one proof that I actually want everybody to watch, and I hopefully do it in it's a very geometric proof, and we draw lots of pictures. I want you guys to make sure you see this. These are absolutely equivalent to find the same line. And notice that only thing that changed is you have to write the function as a function of y, but the guts inside the radical are the same, okay? And so one of the things that's pretty cool is a lot of times we refer to these radicals as ds. So if you're looking in a textbook, right, you'll see like it'll say the integral of something ds. Well, the ds is that radical that they're expecting, but they're equivalent. So you're not constrained here unless it's just algebraically only possible to do the function in terms of x over y, but you can choose either way. So the guts under the radical are going to look the same. But there's a third way. If your curve is parameterized in terms of a third variable, so x is written as some function of t and y is written as a different function of t. So if we plug in time 0, we should be at this point. Whatever time we're done with the problem, we should end up at this point. So this is used a lot in physics. So you have a particle and you're like, well, where is it at time 0? Where is it at time 1? Where is it at time 2? So you plug it into the two equations, and every time you plug in a t-value, you're getting out a coordinate point. It's giving you the point you can plot on the line. So if you want to find the length of something parameterized, right, the integral is going to look like this. So we're going to say that t just goes from some a to b, right? So we would say, well, here the integral is from a to b, right? And in this case, you would say dx dt squared plus dy dt squared, and you would only integrate with respect to t. So you still do the same thing. You take the derivative of each function, square its derivative, and then what you'll see in the proof is that all three of these radicals just come from the Pythagorean theorem. And basically the Pythagorean theorem is just taking, right, the length of the hypotenuse. And so what you're doing is, instead of when you learned how to integrate originally, we had you split the area up into rectangles, and then we sum the rectangles. What we're doing with arc length is we're drawing all these little triangles where the hypotenuse of each triangle kind of hugs the line itself, and we're summing up all the hypotenuses of the triangle. And so you'll see in the proof that we end up getting infinitely many of them, and then that's how we get the true arc length. All right, so the reason this is in this section, which feels like it has nothing to do with what we just did, is for the following. Well, what if I want to take some line segment, right, from A to B, and I want to spin it around an axis? Well, before you were getting 3D objects, right? Because I was spinning a region, a solid region around the line. So we were getting solid cross sections. Now I'm spinning a line around an axis. So what I'm going to get now is just the outside. So this would actually be like a hollow base. So what you would calculate in this case, rather than calculating the volume, right, I'd have to get the whole area if I wanted the volume. Now what we're getting is we can get surface area of any weird 3D shape that we want. And so the surface area, this is going to look a lot like the shell method. What you're getting here, right, are these little bands with width dx. And so what you're getting when you rotate this around is you're getting a cylinder out. It's just a little short cylinder. It's short and fat. So now the surface area would be 2 pi from A to B of the function itself is acting as the radius. And then dx, right, is the line across here is actually our arc length formula. So this guy comes back. And so what this is just like in the shell method, the 2 pi f of x is the circumference around the rotation, and this is the length across or the height of the whole cylinder that you're getting. So this would look like a glass vase with just completely empty on the inside, and we would just want the surface area of the material to build it instead of knowing the volume of the whole solid. And so that means we can write this in variable y as well. If we're rotating something around the y-axis, it would be g of y, 1 plus g prime of y squared. Now, what's crazy about these guys is if I want to measure this around the y-axis, because that radical is exactly the same, because these are equivalent, right, as long as you switch the function, well, what does f of x give you? If you plug a value into the function, what comes out of f of x? The y's, right? So if I want to translate this guy into variable y, well, you grab the y coordinate points, so you would switch the bounds from c to d, y equals f of x, so you replace f of x with a y. And then you replace the radical with the y form. So those are two equivalent intervals. So what's cool about surface area and line integrals is it's a lot easier and more fluid to go back and forth. So this is a horizontal axis of rotation. If you want to do a vertical axis of rotation, think of these guys as the defaults, right? So horizontal axis, that makes you think of x. F of x is sort of the default setting. For vertical axis, right, we would kind of have a y default setting. So that would be the integral of 2 pi from c to d of g of y, right, times this stuff. However, if I want to translate this into variable x, I can. You go back to the x bounds, and in the same way, f of x equals y, well, g of y spits out x values. So you really have 4 versions of this. And the reason you need the 4 versions is algebra. What if you're in a situation where we're going around the y-axis, but the function you have, you can't integrate it in terms of y? Well, now you can flip it and use the x if you need to. You just have to make sure that you understand that f of x is equal to y and x is equal to g of y. So I always recommend that you start with the first 2 equations and you translate over if needed. But so they're really versatile. And so those are the only 4 topics out of Unit 1 that you're going to be responsible for. Just understanding shell and disc and washer, that's just calculating volume, and then an arc length and a surface area. So what we're doing in Unit 1 is all just geometry. How do we get the geometric attributes of irregular shapes, okay? So what's really neat, though, is you can take and apply these same formulas to really basic shapes you know, and the result of the integral is the formula you've been doing since elementary school. So you can integrate a triangle, and if you just leave it as b and h, it'll come out to be 1/2 bh. If you take a circle and you want to integrate the area of a circle, you'll come out with pi r squared. So you can actually generate a lot of these volume, all these funky formulas you grew up using. It's just this methodology, all they did. And if it's a really common shape, we've all grown up using the formulas, but it all came from deriving these integrals out. Okay? All right, so we'll call it for today. Tomorrow we'll look at some Unit 2 stuff.